So one of the things that we're going to come across a lot in basically mechanical engineering are bending scenarios. So we've actually done already a lab where we placed weights on a beam, and typically in real life scenarios, that beam is going to deflect and bend. And when you bend, there's also stress that occurs in the beam. And we can calculate the stress that comes from bending through this equation right here. So when we have a beam bending scenario, so let's actually look and do an example like this. So let's say I have a beam attached here to the wall. I have a force that's applied on the beam, and it's going to deflect as so. The beam has a length. So we have a certain length of the beam. It also is going to have a thickness, and we're going to call this thickness in our coordinate system yx. This is going to be our, basically, at the middle of our beam, in this thickness, we're going to call this the neutral axis. So this is going to be where y is equal to 0. So basically here it's going to be the thickness, or h over 2 plus h over 2 or minus h over 2. H is typically thickness when we look at rectangular beams, and I, which is our moment of inertia, is going to be base, which is the width. If you could imagine the three-dimensional beam, the width in this direction. Base, that's going to be our base. Our height, which is the thickness here, cubed over 12. So that's for rectangular beams. So this, basically, we can calculate the stress here at the top of the beam as a function of this distance y. So plus h over 2 or minus h over 2. And it's going to depend on the moment. So we can calculate stresses in our beam based on this expression. So let's go ahead and let's do an example right now. So we are going to work with a beam that's made of nylon 6/6, so it's a polymer. So our Young's modulus is, our E, is equal to basically 1 times 10 to the 9th Pascal. But interestingly, in our equation, stress is equal to minus my over I. So really, it's independent of our material properties here. We're also given the length, the width, and the thickness. We have our I, and we can calculate y at different scenarios. And we want to calculate the stress at the support of the wall at the top of the beam and at the bottom of the beam. So if we're right here, what is our moment? Well, we have to look at what are our forces. We only have a force that's applied over here. So the moment at this origin is going to be equal to what? Minus our force, which is, we'll call this minus 50 newtons, times what? The length of the beam. So we have our moment, we have yi, so let's go ahead and let's calculate this. So I'm going to quit and clear everything here. And so I can say moment not. Actually, let's define our variables here. So let's calculate. Where are we going here? Our length equals 100 times 10 to the minus 2. Our base is equal to 3 times 10 to the minus 2. Our height, which is our thickness, is equal to 0.1 times 10 to the minus 2. And we should be good to go here. Our moment is equal to minus 50. Let's go ahead and look back down there. Moment, because again, we're going to go into the board. There. So minus 50 times L. And then our stress. So if we do sig top, it's going to be equal to minus m times, now our y is going to be the top of the beam, so it's h divided by 2. And then we need to define our I. Big I. Be careful here, because I is imaginary, so big I is equal to b times h cubed, all this divided by 12. So b times h over 2 divided by I, and then we'll set m naught. Oops. See, big I. Or we could just leave it as little I. Let's leave it as little I. Oh, that's not great notation either. So it's going to be positive. Now, does that make sense? Well, if you think about this beam, right, when it bends like this, at the top, our beam is actually elongating. So if we're in a situation like this where a beam is bending here, this is getting longer compared to our initial state. At the bottom, it's going to be in compression. And we can confirm that by looking at, well, what about at the bottom of the beam? Minus h over 2. Now we're in compression. Fantastic. So that is beam bending in a nutshell. So we'll see you in the next video. Actually, that's kind of essentially the conclusion of this materials lecture. We'll get you into some robotics and controls next, but we're almost there. And I think this is going to be the last concept potentially for your exam. So great. See you in the next video. Thanks. Bye.